Okay, so let's do an example here. So what is the displacement of a boy who walks 15 meters east, 45 degrees north? So that's starting at east and moving towards north, 45 degrees. And then moves 10 meters south, 30 degrees west. So here is my D1 vector. It's 15 meters long, so this is D1. And here's my D2 vector. This is 10 meters long, and they have the appropriate angles on them. Okay, so if I just isolate them, if I was to add them graphically, this is the resultant that I would get, and it would look something like this. Okay, but we want to find that algebraically. So the way that we're going to do that is just in the method that we just showed. So I'm going to break each vector into its x and y components, and then add those x components to each other and add the y components together to get a new vector. Okay, so I can essentially just move everything out of my way that I don't need, and I'll just start with D1. So D1, we need to find what the x and the y components of it are. So this is my D1. Oh, that's the wrong color. This is my D1 vector. And we'll say this angle here is theta, which we know is 45 degrees. So the question is, what are these lengths here? So we'll call this x1, and it's just the length. We know the length of D1 here is 15 meters. So it's the length of D1 times the cosine of theta. So that is just 15 meters times the cosine of 45 degrees. And over here we have y1, which we know is the length of D1 times the sine of theta. And y1 is just 15 meters times the sine of 45 degrees. So that's just, for x1 we get 10.6 meters, and for y1 we get, should be the same, yeah, 10.6 meters. And we'll just take 3 sig figs for now. Okay, so we know that's for our initial displacement vector. So the first little bit of walking that he does. I'll just group all those and move them out of the way. So move this all over here. And now if we look at this vector here, I'll just scroll down, make it easier. So, what do we have? We need to know what this length is, and we need to know what this length is. And we know that this here is the angle that we care about, and this is the length of D2 right here. Okay, so in this case, this is y2, and this is x2. And you'll notice because of where our angle is, that our sines and cosines are going to get flipped in this case. So y2 is going to be the length of D2 times the cosine of theta, which turns into, in this case, is 10 meters times the cosine of 30 degrees. And then x2, in this case, is going to be the length of D2 times the sine of theta, which gives us x2 equals 10 meters multiplied by the sine of 30 degrees. And we just plug that in, we get 10 times cos of 30, say 8.66 meters And here we get 5, we'll say 0.00 meters, which take 3 seconds. Okay, so now we want to know what is our r vector going to look like. I'll group all these guys. Okay, so here was our r vector that we did just graphically by adding tip to tail. And we need to know what is the x and y components of that vector. So what are this value here? This is x of our resultant, and this is y of our resultant. Okay, well, it's fairly simple. All I have to do is for x of my resultant, I take, do it color-coded, I take x1 and I add it to x2. Okay, in this case, that's going to give us 10.6 meters plus, it always gets finicky over here, we had 10.6 meters. And I'm just going to fix this up. So this XR is 10.6 meters plus, and now we have to be a little careful because if you look down here, our x in this case is going in the negative direction. So we're going to have to manually put that in. So instead of 5 meters, we put -5 meters. And that gives us 5.60 meters, sure. Okay, and then we can do the exact same thing for y. And again, we're going to have to be careful because of the direction of our d2 vector. You'll notice our d2 vector, the y component goes downwards, which is the negative direction. So we're going to have to manually account for that as well. So we have y of the resultant is going to be y1 plus y2, which gives us 10.6 meters plus, and it's going to be a negative 8.66 meters. So the y for the resultant gives us 1.94 meters. Okay, so what does that say about our resultant? Okay, well, it says that our resultant here starts at the origin. It's going to move in the x direction. It's going to move 5.6 meters this way. And then it moves 1.94 meters upwards in the y direction to give us this resultant vector here, which we can just call the displacement vector in order to answer this question. So this is our displacement vector d, which was essentially the vector d1 plus the vector d2.